Good morning. You know well that deep learning technologies have advanced a lot through a few past years. And especially the advent of deep learning frameworks such as TensorFlow, PyTorch, or TNO have helped a lot to make these technologies to more people accessible more and more. However, these sorts of technology, like any other complex systems, can't be the sort of, let's say, knobs, or as known as hyperparameter, which should be tuned if one expects to receive reasonable results from these systems. It generally agreed fact that the choice of hyperparameter in systems can lead to the difference between a mediocre or a superior system, or even sometimes state-of-the-art system. However, sadly, there are only a few studies that investigate first, the range of available hyperparameters for each task, and second, to which extent each of these parameters can impact on the final performance. My talk today concerns this issue. I like to provide a list of most important hyperparameters that affects the task, the specific task in text analytics, and also provide an intuition about a priority each of these hyperparameters can play to affect the final performance. My talk is actually the essence of roughly 3,000 GPU hours on more than 500 configurations or rounds. And my hope is that it provides people who have just got their interest into these technologies a fast track, let's say, or an idea about the priority that guides them through the most fruitful ways and help them to avoid the least fruitful avenues. The hyperparameter I'm going to talk about are categorized into 13 sections. First, I'll talk about the embeddings, their size, types, and updating methods, the vector embeddings and their size. Of course, the most important hyperparameters that I'm going to talk are considered deep architectures themselves, their optimizers, gradient control mechanisms, and classifiers. I'll also have a touch on dropouts, the idea of deep versus wide networks, and also talk about pooling and right-sizing the end. The task is a very specific task. You probably agree with me that the results cannot be conclusive, but I'd like to mention that almost all of the findings that I'm going to present you are in line with the few studies that has been done on more studies. So, of course, there need to be more extensive studies to prove the efficiency and importance of each of these hyperparameters, but I hope that these studies provide some insights. The task is a multi-level classification, which you know well. We assign one or more class given each text. We have a middle-sized data set belongs to a company. The evaluation metrics we use is F1 for gauging the throughput of the system, and epochs for assessing the amount of time we need to get the network converged. The methodology is grid search. You observe that we have 13 categories of hyperparameters. Each of these hyperparameters has from 2 to 5 or 6 instances. So you see that forming a grid out of the permutation of all these hyperparameters forms an insanely big grid, which is highly inefficient to search through exhaustively. So we prefer to use ad hoc, where we know that each parameter affects the other and put them on the same grid. So at the end of each grid, I would say that what was the best configuration given that specific grid. The architecture on which we tried these hyperparameters is a state-of-the-art system for the same task, multi-level classification. It's basically another work, of course, and if you are interested, you can check the paper, which is going to be published at ACA this year, and it's also available in archive. But just to help you to have an image about what's going on about the hyperparameters, this is the architecture that we are going to tune our parameters. All right, with all of that in mind, let's get started. One of the most important parameters that we need to set in this study is the embedding size, which is close connection with the type of embeddings. We get statistically significant better result, which is marked by bold font here, by using 100, 200, and 300, and somehow 1024, but the difference between 1024, which belongs to a contextual embedding like called ELMA, is not that much high. Well, it's reported in many papers that it gets the models 2 or 3% boosts in some tasks like NER or quantum speech hack, but in specific tasks, you will see that the difference is not statistically significant. The type of embeddings, of course, we didn't check very fancy or new because it's almost old study. We started from the oldest one, word weight, which is trained on 100 billion words Google News, and moved to GLOBE. We got the best results using the GLOBE 840. We also tried FastText, which basically provides an elegant way for representing unknown words. Or also we tried dependency, which also provides an elegant way to integrating dependency tree, the information regarding the dependency tree into the words. And it turns out that the task which does not require that sort of information, like this task, does not benefit from that sort of data. So people reported in some tasks that they had a large portion of unknown words that FastText worked better than GLOBE. Or some people in some tasks that they require dependency information, such as argument mining or predicate mining. They reported that using dependency-based worked better. However, in our task, we only depended on the words themselves and the connection and their relation to each other, so we didn't get any input on that evidence. And it holds true for Elmo as well, as described earlier. And finally, the method, we had two choices for the embeddings. Either we froze the embeddings and let the model converge, or we let the embeddings get tuned through the training. It's a controversial issue basically in the papers. The rule of thumb is that if we had a large enough data set that could tune the words or embedding code vectors that are already trained over billions of words, all right, that's a good idea to let the embeddings train. However, in small scale, usually enabling either turns to inferior performance or the same performance in our case. So again, we didn't get that much boost. And as you observe, the difference between disabled and enabled mechanism is not statistically significant. So highly probable that the difference, the 0.2 boost, is caused by chance. Two important notions that are roughly new in the area of hyperparameters are the notion of character embeddings, and there are many studies that prove using character embeddings are beneficial. Again, it turns out that it is useful when the information of characters, in addition to the words, would be important in a specific task. For instance, in partial speech type, that the position of characters, suffixes and prefixes, or subwords are informative in the final task. There are studies that show that character engram or any are in hyperparameter recognition that characters information like the position of character or their capital form is important. They proved to be beneficial. In our case, these were not the case, so we didn't get any improvement using these parameters. So we optimize these sorts of character embeddings with the desktop embeddings in 1 week over 14 configuration, and all of them didn't prove any beneficial. Well, moving probably to most important choice to the architecture of the neural network, either as CNN or form of RNN, LSTM or GRU. We use several configuration, LSTM bidirectional, LSTM, GRU, bi-GRU, and CNN. And in all the configuration, around 250, 70 configuration, we did the best results pertain to bi-GRU. Of course, CNN performed very well, but it couldn't beat the performance of GRU. And the issue of controversy against is between LSTMs and GRU. Some people prove that LSTMs work better, some people prove that GRUs are better, some people argue that GRU is much better for short text. Well, there are some discussions. Something that there is definitely is that GRUs are faster than LSTMs, and because of their fewer data, and you see that the GRU performs faster than the LSTMs. However, it's a good idea, in my own opinion, to give these two architectures, these are highly dependent on the task and data sets, give this architecture a chance to see which one performs better. The idea of deep and wide networks are not that new. RNNs and CNNs are already deep. By deep here, I meant using several CNNs or RNN consecutively, and in this way to extract different layers of representation or abstractions from the network. As you observed, we didn't get improvements by adding several layers in depth. We need to, again, to be more task specific. There are some architectures for image processing, for instance, Google Net or ResNet that contain tens of layers in it, and they are state of the art. However, in this specific task, we didn't get that. Actually, we started to overfit after the second and third layer in it. And the same holds true for the number of recurring units. We did the best results, significantly superior results using roughly 100 in number of neural recurrence and using only one layer in depth. Again, these parameters are on the same using the optimizers, the deep and wide and network architecture are all on the same grid with 270 configurations. And well, optimizers, no doubt, are very important. All optimizers except stochastic gradient descent suffer from, which is very sensitive to basically learning rate. All others obtained superior results. We got our best results using Adam and Nadam. The results were almost the same. The difference between Adam and Adam with most of optimization comes mostly through the time required to get the network converged. Basically, Adam, which uses most of optimization, succeeded to converge much faster. We did not noticeable difference in the results. Another important hyperparameter, both in RNNs and CNNs, are potent, which essentially are the same mechanism, not same mechanism, but the same idea. In pooling, again, we got the best results using the notion of average and max pooling concatenated at the end of the layers. gradient control is another important hyperparameter. RNN comes with two critical issues: gradient explosion and gradient vanishing. And gradient vanishing essentially addressed by the idea of introducing gates into RNNs, such as GIUs or LSTMs. However, we have problem with gradient explosion to widely used algorithm, one by Mikolov and one by Pascal, are proposed. In all of our configurations, we got better results using the normalization. So it's again a good idea to first consider using gradient control, and second probably using normalization. And finally, probably the most important layer at the end of the network, which requires deep thinking about the nature of the problem. Not that other parts does not require thinking, but here we really need to deeply think about the thing that we're gonna expect to receive from the model. Either we are interested in a Bernoulli distribution or multinomial distribution, or are the tags in our data set independently distributed or not, conditioned by other tags, or they do. For instance, in tasks that tags are conditioned, like artificial tag, that tags of each token is conditioned by the previous tags. People reported CRF works better, which makes sense because that's designed to do so. However, in our case, which tags were assumed to be independently distributed, we got better result using sigma. Moving to another important hyperparameter, dropout. You know well that neural networks has a high tendency toward memorization, which is not a good thing because we're mostly interested in generalization rather than memorization. And there are few methods proposed to control memorization or overfitting, like A2 and dropout, which proved to be very efficient for controlling the overfitting. Essentially, there are two important algorithms for dropout, or two approaches for dropout. One, the simple or naive, which stochastically remove the link between the layers, and one variational, which systematically removes. And Aghaebrahimian basically proposed and proved that the systematic remove of links between layers works better than naive approach. Both of these approaches can be used inter or intra, either in recurrent layers or between the layers. And in all of our experiments, in all the 90 configuration, we got better results using a variational and both inter and intra layers. And finally, all these parameters leads us to the last one, which is batch size. Batch size is not as important for performance as it's important for the notion of time. So whatever batch size you use, if model works and if it does not overflow or out of memory, it will converge to the, hopefully it will converge to the performance you got from others. But basically, when we choose too small batch sizes, it leads the algorithm to converge much slower. And if we choose the batch size to be much higher, it leads the network to overflow or out of memory. So usually it's some matter of trial and error rather than tuning to consider the memory constraints on the machine which is available to us and choose the highest batch size that are available. And you'll see that in all our configurations, we didn't get statistically significant superior in any of the configurations compared with the others. So that would be the last thing that we need to set before we can get the model trained. All right, then you found it helpful, and I think we have a couple of minutes for questions. Thank you.
Thank you very much, Ahmad. So we have time for questions. Yes,
So
please.
the assumption you make that all these parameters are independent, yeah? So what happens when you get the best setting from all the parameters? What result you get?
Well, the assumption is that they are not independent. Basically, the idea of hyperparameter tuning is to set the parameters in the same grid, all of them, exhaustively, and search that how each parameter change affect the other. But as I described, the permutation for all of these instances are too huge. So we put based on experience, we put the parameters that we think are highly correlated in the same grid, for instance, optimizers, network architecture. And in the same grid, which we set other parameters static, try all these configuration, for instance, 230 something runs, and extract the one which has the highest performance compared to the other.
Another question?
I would have a question about the setup of the network. So you trained on 28 classes. Does that always make sense, or would you sometimes separate classes and train a separate binary classifier just for a certain instance?
Yeah, that's essentially the design choice. So it's in the beginning of the study, we need to provide a network that gives us a rather good results, and hyperparameters comes after. That's another. We can use threshold on the softmax. We can use binary classification. We can use clustering, like you mentioned. But on the part of hyperparameter tuning, we fix the architecture, and on the architecture, we change the hyperparameters.
I have a question about the size of the corpus that you have used.
Corpus is basically a proprietary data set belongs to a company. It contains roughly 60,000 texts. However, the length of the articles are rather high, about 3,000 tokens. And well, it's roughly well distributed. So for at least for each classes, we have roughly 1,000 instances. And yeah, these are characteristics that I remember about the instances.
What is the nature of the classes?
These are environmental threats. It's about the threats that an article can be. Articles are news articles talking about companies, and these companies may commit some sorts of environmental, social, or governance threat, and these classes are detecting what kind of threat each of these articles are talking about.
And labeling is done manually?
Yes, it's done by the company on the part of the company now.
There was a certain measure of annotation agreement on that?
Sadly, no. The approach they choose was to aggregate or use mass intelligence of the all annotations and agreed upon one. So they didn't have different annotations. We were very interested to perform to see how model works in terms of integrating between model and annotators between annotators, but we didn't have that data.
And the performance that we have shown on all the classes are merged together and leveraged on the classes?
These are macro F1, so the average of the F1 over all classes.
I'm curious how you actually implement the Aghaebrahimian search. Like, is it custom code you wrote, or did you use, say, AutoML?
No, it's a custom code.
Okay. So have you considered using AutoML, for example? Because that would also, get around the ad hoc nature and potentially do much more, goal-driven hyperparameter search.
Yeah, there are very exhaustive studies regarding hyperparameters. Some people provided stochastic hyperparameter like Bengio, or some others proposed Bayesian. However, I still believe that ad hoc is more fruitful way to go to the hyperparameters. And essentially, it was not about which hyperparameter tuning works better. It was a need to provide a need to see how each parameter change the performance of others in one group.
And then one follow-up. According to your study, then what would you say if a person is basically, what's the most important hyperparameter? Can you draw any conclusions here? Like, can you rank them or something?
Well, I rather not, because it's highly task dependent, and implicitly I was trying to mention that some of the important and some of the ideas that we need to think about going into implementation, like the distribution we are going to receive from the data, or the nature of data, about the tagging, or the limitation on part of data set, that how it covers the words available in the pre-trained data. So at the end, you saw the results. So at the end, I guess you can extract some of the most performative changes, which starts from probably choice of network architectures, to then kind of classifiers, then kind of embeddings, and finally to drop out and gradient.
So, thank you very much, Ahmad, again.